Good morning, students.
Good morning, sir.
Good morning, sir.
Good morning. So, students, so we will begin with module 2, that is introduction to for master students. This may be a repetition, but for BTech students, I don't think. I think this is the first time they are studying this topic. BTech students, is that correct? BTech students, have you studied parallel and distributed computing somewhere?
No, sir, we haven't had the subject yet.
Okay, fine. So, students, when we studied the cloud computing, basically how it has come, how this cloud computing has come, what is the evolution of computing. If you see the timeline, the beginning was local computing. Okay, informally I'm saying local computing, which means that you have a computer, okay, you have a computer and you load your programs and execute them in a local environment, a local execution environment, or you can say programming environment, and get the output locally. Okay, right. So this was the beginning of computing era, when it became popular to its users. I'm talking. Prior to that, there were computing which was mostly confined to scientific research and other specialized tasks, where the enterprises used to have their own computing infrastructure to execute their specific programs or tasks. But later, when computing became gradually popular and was affordable by the community, so there people used to have their programming environment on their machines, and although the machines were a little larger, and then execute their programs locally on their computers, right? So in that context, we say it began with local computing. Okay, and then what happened, gradually the type of programs started becoming complex, right? So the type, or you can say the nature of computing tasks became gradually complex, and the applications needed more and more computing power and or specialized software. Okay, and these computing power and specialized software were usually expensive and not affordable by a single user, right? So what happened, to meet the increasing computing demand, so to meet the needs of increased computing power, computing power, parallel programming tools emerged. Parallel programming tools emerged, which could run on a cluster of computing nodes, and also on the advanced hardware systems in a time sharing manner. Right? So what we understand by this time sharing manner? What is this time sharing manner? So time sharing manner is something that given a time span, different chunks of time span are allotted to, so this is your CPU time, okay? This is your CPU time, T, and different CPU time, okay, was allocated to different tasks. So these time slots allocated to tasks or programs that are a part of larger program, which means a larger program should be the larger program is breakable. First is the larger program is breakable. So we should be able to break, or the algorithm should be able to break the large program into smaller programs or tasks, and each of these tasks are given different slots of CPU time so that these tasks were executed parallel, which means the tasks, the large program, the requirement is, so requirement for this is a large program should be broken into concurrent programs, which means the smaller programs should be able to run in parallel, or you can say let me do something here. Should be broken into, we'll introduce it later, should be broken into smaller programs. Let's begin with this smaller programs, and the programs, the small programs what you say, the small programs should be schedulable in such a way that the overall efficiency, the overall execution efficiency is increased. What we mean to say here is that when you divide the task, when you divide a program into smaller programs, there may be dependency among the smaller programs. What we mean by dependency is that the output of one program might be needed by another program as input. So in such case, there is a need for precedence in execution of the programs, smaller programs. Otherwise, what will happen? The program which is in need of the output of another program, and if that program is not executed, then the previous program has to wait for the input to be available, right? So scheduling becomes a very important part when you break a larger program into smaller programs and put them into execution, right? So for this reason, task graphs are needed. So task graph depicts, okay, a task graph depicts the dependency among smaller programs of a larger program. So once we know the dependency among smaller programs, we get to know that which program need to be executed first, or the sequence of execution of the programs can be known ahead of time, and they can be scheduled or they can be allocated different CPU slots for execution, so that there will be minimum wait time of the tasks or programs, right, that would have needed had we not scheduled based on a task graph. Clear, students?
Yes, sir.
So this is popularly referred as sequential programming. Sequentially programming because the tasks are entered into the CPU or scheduled on CPU in a time sequence, based on the task graph, right? So the overall job turnaround time or overall program turnaround time will be the sum of times spent by each small program while executing on CPU. But everything will happen in a sequence. There is no parallelism involved here, one after another in a time sequence. So what happened? This happened in a uniprocessor machine. Machine because there was only single processor, and which was receiving the programs in a predefined sequence, and each of these programs was executed on the uniprocessor machine depending on the amount of time allocated to these programs, right? Later, people thought of reducing this overall job turnaround time or program execution time further with the advent of multiprocessor systems. Okay, so conclusion here is the uniprocessor machines executed the programs in a time shared manner sequentially, leading to you can say increased program turnaround time, right? So uniprocessor machines executed the programs in a time shared manner sequentially, leading to increased program turnaround time. Subsequently, with the introduction of what we say multiprocessor systems, multiprocessor computers, the program execution scenario has changed in terms of overall program or job turnaround time. Right? So what is a multiprocessor computer? Uniprocessor computer will have only single functional unit. Single functional unit, in the sense that there will be one functional unit which will be executing all types, or you can say there will be one addition unit, one multiplication unit, right? Like that. So uniprocessor. So when you have multiprocessor computer, so there you will have multiple functional units, and these functional units are interconnected through system bus, right? Or processor, interprocessor, multiple. You have dual core processor, quad core processor, octa core processor. So these are all examples of multiprocessor computers, which is within one single processor you have multiple cores of uh, computing elements, and these cores are again interconnected, and each of the core is a processor in itself. So just for the sake of understanding, you can think of a multiprocessor computer as having multiple functional units. So the benefit of having multiple functional units is that one functional unit, while it performs some operation, or you can say that a program having multiple functional units or functional what you say logics can be executed in parallel in case of a multiprocessor computer. So executing things or executing programs or functions in parallel has reduced the overall program turnaround time significantly as compared to executing the functional components of a program in a sequence, right? So here things are happening in with parallel, and there it was happening in a sequence. So because these programs are parallelly executable, okay, of course, under the assumption of the task graph, which allows the wherever a parallel execution is permitted. So task graph will say you which functional components are independent of each other and so are parallelly executable. Only those program components can be executed concurrently in a multiprocessor computer. So as a result of this parallelism, the overall program or job turnaround time has come down further compared to a uniprocessor system, right? So technically we say that speed up is achieved through multiprocessor systems vis-a-vis uniprocessor system. So one may ask that what amount of speed up is achieved? What amount of speed up is achieved? Yes, students, what amount of speed up is achieved?
The processing speed. Task
Yes.
completed. Task completed in less time.
what amount of speed up is achieved? What is speed up? So what is the maximum value of speed up? What can be the maximum value of speed up? One or not?
Yes, sir.
Speed up factor is 1 maximum. So speed up is nothing but the ratio between what? Anybody? Anybody, students? So ratio between what? Time or task? What it is? Ratio between?
Sir, task upon time.
How can it be? Speed up is a factor. Factor will have no units. Speed up will have no unit. So if you take task over time, then it will be 1 upon t will be the frequency. Are you getting? So numerator and denominator both terms must be of equal units.
So sequential time upon parallel time.
Yes, yes, perfect, perfect. Who is that? What's your name?
Bharat.
Bharat. Okay. So speed up is the time versus time, right? So you can say that if you are taking a k-stage pipeline processor, then speed up will be defined as that the what is it that in case of non-pipeline, T non-pipeline pipeline to T pipeline, right? So the time taken in case of a non-pipeline machine to the time taken in case of a pipeline machine, right? That is nothing but the speed up. So both are time will get cancelled and you will get non-unit measure. So if you are talking about a time taken in a non-pipeline, and I'll put that n number of tasks and k number of stages. And let's say these are the stages, these are the CPU, okay, these are the stages. So tasks enter this way and exit this way. So tasks enter and exit, right? So these are k stages, and this is stage 1, stage 2, stage 3, stage 4, stage 5, and so on, right? K stages, and n is the number of tasks. So in case of a non-pipeline, if you are saying that it is going in a non-pipeline fashion, in a sequential fashion, then each process each program has to cross k stages before it is output of the system. And if there are n tasks, so it will take n into k amount of time. Is this clear, students? Nk. So T non-pipeline will be Nk divided by the first task. The first task that enters here, the first task that enters has to go through k stages first, right? K stages. Correct hai ki nahi bachcho? The first task that has to go through k stages. So k तो एक जरूरी है, time plus, और हर स्टेज का टाइम हमारा कुछ डिफाइन है, तो k स्टेज के लिए k टाइम्स हो गया, ठीक है। प्लस जो दूसरा टास्क हुआ, बिकॉज इट्स अ पाइपलाइन, सो जब पहला टास्क यहां से यहां तक चला गया, फिर ये जगह खाली हो गया, तो दूसरा टास्क आ गया, T2 आ गया, फिर ये T1 यहाँ पे आ गया, ठीक है। फिर ये क्या हो गया, T2 यहाँ पे आ गया, T1 थर्ड पे चला गया, T1 थर्ड पे चला गया, और फिर T2 यहाँ चला गया, तो ये जगह पे क्या आ गया, T3 आ गया, और यहाँ पे T2 चला। सो इस तरह पैरेलली ये एंट्री हो रहा है। तो फर्स्ट के लिए तो आपका K चला, K स्टेजेस, और बाकी के लिए सब्सिक्वेंट के लिए कितना होगा, इट विल बी n-1, ठीक है। सो योर स्पीड अप विल बी nk over k plus n-1। इसको एक्सपांड करोगे तो पता चलेगा तुम लोगों को कि अगर 4 टास्क अगर लोग, एक एग्जांपल लेके देखो, 4 टास्क लेके देखो, और 4 स्टेज या 5 स्टेज का सिस्टम लो लेके देखो, टोटल कितना टाइम लग रहा है टी पाइपलाइन में और नॉन पाइपलाइन में। दैट विल गिव यू द एस्टिमेट ऑफ स्पीड अप, ठीक है। कोई क्वेश्चंस स्टूडेंट्स? Students, any question?
No, sir.
So what we have observed here is that through pipelining or through uniprocessor system, we have achieved some amount of speed up compared to its uniprocessor system. In multiprocessor, we have achieved some amount of speed up compared to its uniprocessor system, provided that the task graph has the jobs concurrently executable, ठीक है। that is the underlying assumption. तो फर्स्ट केस में यूनिप्रोसेसर था, फिर मल्टीप्रोसेसर आया, मल्टीप्रोसेसर में पाइपलाइन के थ्रू से हम लोगों ने स्पीड अप अचीव किया। फिर तुम्हारा यहाँ पे तुम्हारा पैरेलल प्रोग्रामिंग चालू हो गया। सो because of the concurrent execution of programs, ठीक है, that are, I'm writing, that are as part of a larger program, okay, because of the concurrent execution of programs on a multiprocessor सिस्टम। देखो यूनिप्रोसेसर सिस्टम में भी पैरेलली एग्जीक्यूट हो सकता है, लेकिन उसके लिए अलग प्रोग्रामिंग एनवायरनमेंट चाहिए, ठीक है। बट मल्टीप्रोसेसर सिस्टम में कन्वीनियंट तरीके से एग्जीक्यूट हो सकता है, राइट। सो बिकॉज ऑफ द कंकरेंट एग्जीक्यूशन ऑफ प्रोग्राम्स ऑन ए मल्टीप्रोसेसर सिस्टम, parallel computing paradigm saw, you can say, saw new developments in the sense of newer hardware architectures, and advanced parallel programming paradigms, etc. Right? So this helped the parallel computing to become popular in the science, and it became cost effective. Right? So examples of parallel computing infrastructure are supercomputing, supercomputers. Right. So these supercomputers were having a number of processing elements or computing elements or CPUs, with interconnected CPUs, and arranged in a rack, and large scientific programs or problems were executed on this. So it looked like this. So a supercomputer will have several cells, and these cells will have these computing nodes, number of computing nodes, and these computing nodes are interconnected, or you can say these CPUs are interconnected. So these are CPUs are interconnected through low latency or high speed interconnects, right? Interconnects. And there used to be a central scheduler. So the tasks are, or programs, large programs are scheduled here, and the central scheduler generates the task graph. Okay, or you can say that while scheduling, when you say scheduled, then basically we are saying the task graph. Break the program into smaller programs and create a task graph and submit it to the central scheduler. And these smaller tasks will get scheduled on these CPUs. Okay. So the parallel through parallel processing, you are getting the results quickly. Okay. But the major drawback of this was that if the program is too large, then the supercomputer was utilized to a maximum extent. But if the program is small, then small in nature, then the supercomputing system was too large for the small program to execute, so resource utilization was less. Moreover, these supercomputers were not publicly accessible. These were confined to the uses of scientific organizations or the organizations who could afford to buy those supercomputers, right? So the computation needs of people were not met by these supercomputing infrastructure because these were not publicly accessible, right? So these are also known as the cluster of computers or cluster computers, cluster computing infrastructure. So supercomputer is an example of cluster computing infrastructure. So to make the computing more accessible, people thought of breaking this supercomputing era into a distributed computing, right? So here also the computing is distributed. If you see here also the computing is distributed because the tasks are distributed across multiple computers or multiple CPUs. So in that sense, we say that this is also a distributed computing setup. However, this distributed computing setup is under the control of a single central scheduler. Okay, So we also refer to it as a tightly coupled system. We also refer to it as tightly coupled system. So this kind of distributed processing happened over a tightly coupled system setup, right, which was very expensive and not publicly accessible. So to make distributed computing, processing happen over a loosely coupled setup, the concept of grid computing emerged. So in this grid computing, several off the shelf computing machines, computing devices as part of the internet infrastructure were allowed to execute the tasks, So these distributed computing devices, okay, so these are geographically distributed computing resources. These are geographically distributed computing resources, and of course they are interconnected. Something like this: distributed, interconnected computing resources. So the job was scheduled. So there is a gateway to this infrastructure, to this distributed infrastructure, and large programs were input. So large programs are input, and there is a what to say, resource management system. Okay, there is a resource management system which hides the underlying distributed interconnected computing resources from the user. So it plays as an interface between the user and the underlying geographically distributed interconnected computing resource. So when the user submits the job, the resource management system has a number of functionalities built into it. Okay, so this is essentially a middleware system or middleware which has a number of services. Middleware that has a number of services designed to handle the needs of distributed computing paradigm. Okay, so this resource management system takes the program and finds the resources that are required to execute the program, negotiates and collects the results and give it back to the user. So that is how the user's need for large computing infrastructure was made possible through this off-the-shelf geographically distributed connected computing resources in very cheaper price and ease of accessibility compared to its supercomputing or cluster computing counterpart. Yet this was able to achieve achieve the performance similar to the cluster computing, right? So in this journey we saw three things. One is we began with uniprocessor machines, computing in uniprocessing paradigm, and then we evaluated that and moved on to the parallel processing paradigm, where we saw that the speed up is achieved compared to uniprocessor, but it was a bit expensive, okay, and it has some more disadvantages. Then we moved on to a better distributed system known as grid system, or grid of this grid of computing resources, or which can be seen as a geographically distributed interconnected computing resources, which further reduced the cost of computing and enhanced the infrastructure utilization, right? So this is the next step. Then the next step is the cloud computing. Cloud computing paradigm. Cloud computing paradigm we have discussed in previous 3 to 4 classes. This is also a distributed paradigm, wherein, as opposed to or as compared to grid, where the resources may be owned by people like you and me, whereas in cloud computing the resources are mostly owned by enterprises offering the cloud computing services, as we studied infrastructure as a service, platform as a service, and what's the other one? IaaS, PaaS, and software as a service. So these facilities were provided by cloud. So cloud computing paradigm has emerged as an enterprise compared to grid. Grid could not go to that enterprise level because of you can say the diversity involved, and business houses saw more business potential in cloud computing paradigm compared to grid computing paradigm. So grid computing could not take an enterprise state of operation, whereas cloud computing could. So cloud computing also offers the facilities similar to grid computing to its users in a much cost-effective manner, right? Is this clear, students?
Yes, sir.
Then comes your fog computing. fog computing paradigm, wherein a fog of, it's a virtual computing layer is seen in between cloud and the user. This is also a part of distributed paradigm. Now the latest is the edge computing. Latest is the edge computing paradigm, wherein the computation is further brought into the close proximity of user or the point of data generation. So if you see the evolution of various computing paradigms, the first was the local computing system, then it became a uniprocessor, multiprocessor system, then your cluster computing or supercomputing era, then cloud computing era, then fog computing era, then edge computing era. So the future, which will have your vehicle to everything, vehicle to vehicle, and all these mobility associated, computing associated with mobility, will try to execute most of its computing needs at the point of data generation. Thus the terminology referred to as edge. Right? And during this process, lot of communication, computing issues will arise with respect to the distributed computing paradigm. It's a huge area, and we don't know, I mean, it will dominate the computing communication world for another 30 years at least. Okay, so students, I think we have discussed many things in this class. I hope you got a good visualization at least about where do these computing paradigms rest and how are they related, or how are they different, if at all, right? So you require to culture more on these computing paradigms, at least to have an introductory level clarity. Okay, any questions, students? Students, any questions?
No, sir.
No, sir.
So we'll break here today's discussion. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.